For instance, for some reason, we want to prove that x and y are both not equal to 1 in the nested ifs. And since this point is just outside the feasibility region, then we have guarantees that this is never going to happen. So there are many different numerical abstract domains that have been proposed in the literature. One of the first ones, and probably the simplest one that you can have, is just the box domain, which only keeps, instead of keeping just the constraints of the values of the variables, it keeps the upper and the lower bounds of each variable. That's why it has like this box shape. And one of the most expressive ones is the polyhedral domain, that it really takes any linear constraint that you can have between variables. And between this very simple and very fast box domain and this very expensive polyhedral domain, there are many abstract domains. For instance, zone, octagon, TVPI, and octahedron. And what this talk is about is about this TVPI, which basically stands for two variables per inequality abstract domain, meaning that in each constraint you only allow two variables to be in the constraint itself. Not like in the polyhedral, where you will have like arbitrary number of variables in each constraint. Okay, so let me go back to the previous example that we had before, but now assume that x and y are double precision floating point variables instead of integers. So what would happen for this case? Well, at the beginning it's just the same. X and y can take any possible values in the domain of double precision floating point numbers. But once you go a step further in the program inside the first if condition, I mean, you are tempted to do the same as before, just adding this constraint in order to reduce the feasibility space. However, this is not sound for floating point programs. And the reason is that you have round of error. This x plus 2 is not just x plus 2, it's s plus 2 plus some rounding function that you can have afterwards, because floating point has a limited precision. And this is usually solved using round of error linearization. What I mean with this is that instead of just having the constraint with x plus 2 in this case, you would multiply this operation by this gamma. And this gamma is just a very, very tiny interval around 1, which models the round of error that you can have. And this is not sound. This constraint is not sound. And if you were to plot it, it would look more or less like this. So the limitation of the traditional integer abstract domains is that they cannot really represent these kind of constraints, because these constraints now have interval coefficients for the variables, whereas the traditional ones only allow for a scalar coefficient. Also, you can see it slightly in the picture, but also having these interval coefficients allow for non-convex shapes. I mean, you can see it a little bit, the non-convexity in the shown plot. Also, usually the abstract domains are implemented using rational arithmetic, and we aim for a fast implementation using floating point arithmetic in the implementation itself. So in order to do this, we propose a new abstract domain, that we call TVPI-FP. And TVPI-FP, what it does is the same concept as the TVPI domain, two variables per inequality. However, we allow interval coefficients to occur in these inequalities, in these constraints. And here you can see just an example of how two inequalities would look and the feasibility space that they would show. Some of the features of our new abstract domain is that it now can model these non-convex shapes that are common due to round-off errors in floating point programs. We support common operators for program analysis, such as join, meet, widening, inclusion test. We also support elementary functions, which are common in floating point programs, and these symbolic values, such as nans and infinities, in our abstract domain. And last but not least, we implemented it using floating point in its implementation itself, in floating point with interval arithmetic, to allow for a fast implementation. One of the main challenges when implementing and when designing this new TVPI-FP abstract domain is to handle in a sound way the non-convexness of the intervals inequalities that we allow in the operators, because now we have inequalities with interval coefficients. So for example, just in the join operator, just as it's done in the standard integer TVPI, is that if you have two polyhedral and you want to compute the join, you first translate into their generator representation. And the generator representation is just translating the interval coefficients into a representation of only vertices and arrays. In this case, there are only vertices for both polyhedral. Now, over these two sets of vertices, you can compute a convex hull. You can identify the vertices that are part of the convex hull, and then you can convert back these vertices back to inequalities, to constraints, basically. And this works properly for the integer TVPI. However, for TVPI-FP, for the one that we propose, there are cases where the convex hull would not yield anything, like any constraint, because the shape of the joint is non-convex. For instance, if you have these two polyhedral, I mean, you can see that there is no convex inequality. There is no inequality with the scalar coefficient that could include these two polyhedral. So in this case, we modify the algorithms of the original TVPI, or we adapt them to handle also, or to compute also, hulls that are not necessarily convex. In this case, for this particular example, I mean, we can just compute the join by adding an inequality that covers P1 and P2, and this interval inequality is not convex. And another challenge arises due to using non-interval arithmetic in our implementation of the operators. So this happens when performing an interval comparison, for example, and this comparison has an unknown state. What I mean with an unknown state is, for example, if I do this operation, just the interval between 0 and 2 is less than 1. Clearly, there is not an answer, a true or false answer for this, because 1 is included in the interval itself. So the left-hand side is not less than, neither greater than 1. So I will give an example of where this occurs in our implementation. So in the algorithms, we compare a lot the angles of the inequalities. And for example, when you have this inequality, just y less than 2x, and this is the feasibility space, then the angle is just based on the x-axis, and you can calculate it just with the arctan of the coefficient of x for this particular inequality. So this angle is 63 degrees. However, this is using scalar constraints. Once you have interval constraints, if you repeat this process, you would get the arctan of an interval, which will give you an interval of angles. And these angles are between 27 degrees and 63 degrees for this particular interval inequality. So what I mean with this is that not only we have interval inequalities, but when calculating, performing the algorithms of the operators with these interval inequalities, we also arise with interval angles of these interval inequalities. And the reason why I mentioned this is that this occurs, for instance, in our join operators. When we calculate the generator representation that I mentioned earlier, there is one place in the algorithms where we compare the angles of two inequalities and we check if the difference between them is larger than pi. If they are, then we decide whether to add a vertex or if we should add array for the generator representation. And in this case, if this comparison yields an unknown state, we have to make a decision. And we have different ways to handle this unknown state. And the first one that we try to do is to make a decision that preserves soundness. For this particular example, adding array is sound instead of a vertex. So this is what we do in the highlighted blue statements in the code. Another possibility is to evaluate using this joint representation. So I will not go into this part further, but this joint representation is a way to translate an interval inequality into 4 scalar inequalities that form a disjoint between them. And finally, another way to handle these cases when we have a known state is just to drop the problematic constraint that is giving rise to this unknown state. And dropping constraints is always sound, but we try to avoid this as much as possible because we lose precision the more we drop constraints, of course. Okay, we go now into our evaluation section, and we compare TVPI-FP with other tools to analyze floating-point programs. In particular, I will show the results against bots, DAISY, and Fluctuate. And Fluctuate uses the sonotope domain, whereas DAISY uses the box domain, but it also incorporates SMT solvers in order to shrink even further the ranges of the variables. All of them support elementary functions. DAISY only partially supports branches and loops, whereas we are the only ones that really truly support non-convex shapes. We do experiments with 62 benchmarks, where each benchmark is just a function that specifies ranges of its inputs arguments, and it returns a floating point result. And the accuracy we determine using what we call the improvement factor, where that is basically the range returned by bots in a benchmark divided by the range of the tool. So basically, we're using the bots domain as a baseline to determine how much to improve compared to the bots domain. So an improvement factor of 2 simply means that the range is half of that of the bots domain. And in terms of accuracy, at least, we see that TVPI-FP achieves an average improvement factor of 1.46. DAISY, it uses SMT solvers, is slower, but it's more accurate with 1.65 improvement in average, whereas Fluctuant only 1.25. So all of them improve over box, of course, they are more powerful. But another interesting thing is that out of benchmarks that consist of branches and loops, we improve over bots in 80% of the cases, whereas, for instance, Fluctuant only improved for this set of benchmarks only in 29% of the cases. In terms of runtime, TVPI is way faster than DAISY because, as I already mentioned, DAISY uses solvers, so it's between 1 and 4 order of magnitude slower, whereas Fluctuate is actually faster, it's 4.6 faster on average. So in general, it's kind of a trade-off between accuracy and performance. And with TVPI, we position ourselves in I think, a sweet spot between these two factors. And just to show the whole glory of our experiments, we also compare with other tools, but I think I just summarize like the most interesting bits of information. But you can see all the details in the paper regarding our improvements and the timings and how fast we are or slower than other tools. And thanks for listening. This concludes my presentation. And just as a reminder, what I presented is TVPI-FP, an abstract domain for the analysis of floating-point programs, which allows interval inequalities. It is implemented using floating-point, and it supports elementary functions. I presented also some of the challenges that we encountered when implementing and when we designed this abstract domain, and I showed an evaluation compared to similar tools in the literature. Thank you.
He can hear us, so you can clap. Okay, Joao, you are there. That's great. So anyone want to ask a question? Now he can hear us. And so come up and ask your question.
Hi. Fascinating talk. Awkward question. What about widening? Is there a useful widening algorithm for TVPI-FP?
Yes. Actually, we use the same widening algorithm as in the integer TVPI. Maybe the only difference in widening is that we cannot do some of the optimization that they do for integers. But basically, the high-level algorithm is the same as integer TVPI, which is basically, if you want to apply widening, you just remove constraints that you know that are problematic for widening. So it's basically you lose a lot of precision, and that's why in some of the benchmarks where we have loops, we see that we lose a lot of precision from the beginning, and we don't see any much gain compared to bots, because widening is in general, I mean, just loses precision a lot. Yeah.
Okay, brilliant. Thank you.
Joao, you mentioned a whole list of benchmarks. In which language are those benchmarks written?
Yes, these are C benchmarks. We took most of them from FP Bench, which is like a standard benchmark for floating-point programs, and some of them are from previous papers also related to the topic.
Very good. All right. I think we have exhausted our questions. Thank you very much for participating online.
Yeah, thank you. So bad that I couldn't be there physically, but yeah, nice to be here. Bye.